let's take a look at an intuitive, what I think is kind of an intuitive approach to the dot product. Now, it's perhaps most intuitive to connect the idea of the dot product with force and the amount of work done. Now, work is defined as the magnitude of displacement. If an object weighing 10 newtons, as an example, is pulled over a distance of 30 meters, and we're going to ignore friction here. So I've got this thing with a weight of, say, 10 newtons. And we're going to pull it over a distance of 30 meters. Then what we say is that the amount of work that's done is going to be, whoops, this should be a 10. I should put a little n here for newtons. It's going to be 10 newtons times 30 meters, which is going to be 300 newton meters. That's the amount of work that is actually done. So think of the vector d as a displacement vector, and F as a force vector pulling at an object on an object at the angle theta. Now, theta is kind of small here. Let me fix that so you can tell. That's actually theta there. From the direction of displacement. So I'm pulling at an angle theta from the direction of the displacement. Now, the total amount of work that is done is in the component of the force vector in the direction of the displacement vector. And it's going to be multiplied by the total distance d. So let's draw a little picture of this real quickly here. Let's say I have this force vector, and it is at angle theta to the displacement vector. So I'm displacing the single point. Let's say there's a point object right there. There's a little object there. And I'm pulling it in that direction. The force is being applied in that direction. And the displacement is in this direction. So maybe this is a frictionless surface. And we're ignoring friction here for all these examples. You get into physics, and then you start taking a closer look at the idea of coefficient of friction and how that plays a role. But right now we're ignoring the idea of friction. So this is some object on a frictionless surface, and the force is in this direction. It's going to move in this direction. So the amount of force that is in the same direction as the displacement vector, if I drop a perpendicular, I can represent that as this vector right here. Now, the magnitude of this vector is going to be the magnitude of the force vector. So the magnitude of F times cosine theta is going to be the component that is in the same direction as the displacement vector. Now, think of this thing, this component down here, this is actually a projection. And what we want to do is think of this as, let's say, as a projection of F onto this vector D. Think of it perhaps as a shadow. That's one way it's very commonly described, the shadow of F onto D. Okay, so where are we here? The total amount of work, which is going to be a scalar, W, is then going to be equal to the amount of force in the direction of the displacement, which is the magnitude of F, times cosine of theta. I'm going to multiply this. This is the total amount of force that's being applied over the total distance. Well, the distance is going to be the magnitude of the displacement vector. So work is going to be the magnitude of F times the magnitude of D times cosine of theta, where theta is the angle between the force and displacement vector. Now this actually is going to lead us to the idea of our definition of a dot product. The dot product of two non-zero vectors, say vector A and vector B, is the number, and I'm going to write this, see, A dot B. When we see this dot, which we typically think of as multiplication in algebra, beginning algebra, when we're using this with vectors, this is referred to as the dot product, and it's read as A dot B, understanding that both A and B are vectors, is equal to the magnitude of vector A times the magnitude of vector B times the cosine of theta, the angle between A and B. Now, notice that all of these are all scalars. When I say all of these, I'm talking about all these on this side. The magnitude of A is a scalar, magnitude of B is a scalar, and cosine of theta is a scalar. Therefore, the dot product is a number. When you're done with it, it's not a vector, it's a number. And one interpretation, we can actually interpret B dot A in exactly the same way, because A dot B and B dot A, because they're scalars, are actually going to give us the exact same value. If I go back up to here, and if I think of F, well, the work is going to be F dot D, which is, like I wrote, the magnitude of F times the magnitude of D times cosine of theta. Well, if I think of this as D dot F, well, these are scalars, so this is going to be the magnitude of D times the magnitude of F times cosine of theta, which is the same as the magnitude of F times the magnitude of D times cosine of theta. So these values are going to actually end up being the same thing, whether I do A dot B or B dot F, or up here D dot F or F dot D. So I think I've said an F down here. It should be A dot B and B dot A are actually going to be the exact same thing. Now, something that's kind of important here to note is if cosine of theta is greater than 0, or cosine of theta is actually greater than 0 for the angle 0 less than or equal to theta, which is strictly less than pi over 2. So if my angle is between 0 and pi over 2, therefore, or then A dot B will also be greater than 0. Now notice that cosine of theta is strictly less than 0. For pi over 2, less than theta, which is less than or equal to pi. Therefore, A dot B, or B dot A, is going to be less than 0. It's going to end up with a negative number. So because of this, let's just draw real quickly here. If this is the direction of my displacement vector, see, any force vector in this first quadrant here, all these are force vectors, are going to end up with a positive dot product. However, any vector in this quadrant, these are all force vectors. Again, just as a reminder, this is going to be 0 degrees. This is pi over 2. This is pi. So anything in this quadrant, I'm going to end up with a negative dot product. Now, what that does is we can also think of the dot product as being a measure of, let's say, how vector A and vector B are aligned with each other. Because clearly, if the force vector is in the exact same direction as the displacement vector, then cosine of theta is going to be 1. That's perfect alignment. Up here in the first quadrant, it's not quite as aligned. Over here in the second quadrant, this is going to give me a negative cosine, so the force is in the opposite direction, which again tells me about the alignment. Now, an interesting result from this, which you can probably see already from the diagram, is that it can also tell us if two vectors are orthogonal. And orthogonal means they're perpendicular to each other. Now, they're going to be orthogonal if and only if A dot B equals 0. Well, see, if my force vector was here at pi over 2, cosine of pi over 2 is 0. So in that case, I would have, let's say the work is going to be the magnitude of A. I'm not sorry, let's get rid of the A. Let's take magnitude of F. And this is now my force vector, so I'm going to say F is up in this direction with an angle of pi over 2, times the magnitude of the displacement vector, times cosine of pi over 2. Well, it doesn't really matter what these vectors are, because cosine of pi over 2 is 0. So this equals 0. If I'm pulling straight up, I'm not going to have any force in the direction of the desired displacement, so I'm not going to get any movement in that direction. So that's telling us that this is in fact a right angle, and the only way that can happen is if the dot product is 0.